Hello, Dr. Cook here. Today we're going to be talking about vacuum trajectories. The vacuum trajectory starts out with a couple of assumptions. Now I want you to go ahead and pause the video and think to yourself, what assumptions might we be making if we're looking at a trajectory in a vacuum? So think about that. All right, so our assumptions start out with we're in a vacuum. That means we have no air. If we have no air, that means we have no drag. All right, the next assumption we're going to make is we're dealing with a point mass. All right, there's no body effects. Our entire projectile is just a point in space, so orientation, rotation doesn't matter. And the last one is that we're going to neglect the Earth's rotation. All right, in these analyses, we're just in a space, and the ground underneath us is stationary and not moving, which will give us some kind of free body diagram like this. We have a point mass, and we have one force acting on it, the force of gravity, which is the mass times the gravitational acceleration. All right, starting from that free body diagram, we can start out with something very simple, that our accelerations in the x direction is equal to 0 because there's no forces acting that way, and our acceleration in the y direction is negative g, the acceleration of gravity. That's the only thing acting on our body in a vacuum. Now, if we integrate those for time, we can go from acceleration to velocity. So velocity in the x direction at any given time is a constant, which is going to have to equal the velocity in the x direction, all right, at time equals 0. And if we integrate the acceleration in y, we'll get a velocity in the y that is negative g times time plus some constant. All right, now that constant is going to be based on our initial velocity times the sine of our launch angle. All right, and we can do the same thing for x. All right, so our velocity in x will always be the initial velocity times the cosine of the launch angle. All right, that is the x component of the initial velocity. So if we take our velocities and we integrate them one more time, we will be able to get position. So our x position at any given time is time times our initial velocity times the cosine of the launch angle. That's equation 9.3. And in the y direction, y at any given time is our initial velocity times time times the sine of the launch angle. But now we have to say minus 1/2 gravitational constant times time squared. That's equation 9.4. So that gives us a set of equations for where in x and y the distance downrange and the elevation we're going to be at. But we can take the two of those and combine them and get a relationship between them, and we can define our y at any position x downrange. All right, and then we get this equation 9.7 from the book. All right, so if we want to know what will our elevation be when we're 100 meters downrange, maybe there's an object there, we want to know if we're going to go above it or through it, we can assess that. Now, from those parametric equations, we can get some, simpler equations derived for some key things that we care about, such as what's the maximum range that I could possibly hit. Now, we know that max range will happen when we're at a 45-degree elevation on our launch angle, and is going to be at y equals 0 when we return back down to the ground. All right. So if we start out with y at our maximum range, all right, this is the same equation before, just with max range plugged in, and we know that those launch angles have to be 45 degrees, all right, then we can say, hey, that has to equal 0 for our y value, which gives us this equation. All right, we can simplify a little bit. Now, when we look at this, we can say that the x's cancel out on each side there, so we do that. The tangent of 45 degrees is 1. The cosine squared of 45 degrees is 1/2. All right. Now, that 1/2 is going to cancel out with the 2, all right, which can then simplify down to this. G of x max equals our initial velocity squared, and solving for x max, all right, we get equation 9.12. So as long as we know our initial velocity and what the gravitational constant is, we can get a theoretical maximum range that we could possibly hit with that gun system. All right. Now, if we change the elevation, we will get other ranges, but they will have to be less than the maximum range. In a similar way, we can get the maximum altitude, all right? And we know that the maximum altitude will happen when we're halfway downrange, right? So what is our x max over 2, all right? So y at 1/2 max range, right? And then we can plug in that value that we had where the max range is velocity squared over g. So we put the 1/2 there and substitute that into our initial equation. All right, the tangent of 45 degrees is 1. The cosine is 45 degrees squared is 1/2. Cancel out the 2's. All right, and then we can rewrite that in this format where we took the squared value and carry that out. All right. Now our v naught squared will cancel out with 2 of them from the top. All right. The g can cancel out with that g squared. And that gives us this simplified version. 1/2 v naught squared over g minus 1/4 v naught squared over g. Written another way, 1/2 minus 1/4 times that part, which just equals 1/4 times initial velocity squared over g. So our y maximum, all right, theoretical, will always be velocity squared divided by 4 times gravity, and that's equation 913. All right, but what if our target isn't at maximum range, right? We want to know how to hit a target at a certain place, okay? So if we're starting from range, we're going to want to know what launch angle do I need to be at to hit that thing, right? So we know that y equals 0. What angle do we want? We're going to start with 9.7 with y of x equal to 0. And then we're going to solve for the launch angle. All right. So launch angle for some given range to target is 1/2 the arc sine of the gravity times the distance divided by the initial velocity squared. We might also want to know time of flight. So when you call in for artillery fire, right, we call in our fire mission, and the FDC is going to call you back and say shot over, right? You say shot out. And then they call you a little while later to tell you splash over, and you say splash out when you saw it land. Well, how do they know when to call you that and let you know to look for it, right? They got to know the time of flight. So that's what this is about. So we figure out how long is it going to take to get there. It's especially important if we're trying to hit a moving target. Again, we want y equal to 0 because we're back down to the ground. We're going to start with that equation 9.4, and we're going to solve for time. All right, and that'll give us this time of flight equal to 2 times the initial velocity times the sine of the launch angle divided by the gravitational constant. That's equation 9.22 in the book. All right, last I want to talk about a special case of vacuum trajectories, which is the flat fire vacuum trajectory. All right, make sure you catch that. It's the flat fire vacuum trajectory. All right, so this is some specialized equations if we're looking at launch angles that are less than around 5 degrees. All right, if we look at that cosine squared of 5 degrees is very close to 1, and that tangent of 5 degrees ends up actually being a number, right? It's at 5 degrees is 0.08. All right. So knowing that information this is kind of like rifle fire, right? We're not really elevating our gun like a howitzer or mortar. We're just shooting at targets like if we've got a rifle or a tank or something like that. All right. So we can take that and it will simplify our equations a little bit to get those cosines out of there. So our y at any given distance downrange is approximately equal to this equation here. All right. So now tangent of the launch angle is the only trigonometry we need to worry about. If we say y equals 0, we can find an x max value. All right. That is simplified for flat fire. And we can also say, hey, what launch angle do I need to be at to hit my target at a given range, right? Which is based on the arctan of the gravity times the range divided by 2 times our initial velocity squared. All right. And with that, I'll see you all in class.